All right, thank you all for being here bright and early, first day of conference. I'll go ahead and kind of describe the work that we've been doing. Research is mostly conducted by my PhD student, Masoud Ferriman, whom I like to acknowledge, and we have a surgical collaborator, Mino Cavarana. Okay, so this is the Fontan circulation. Compared to the normal circulation, so here's normal, you've got a right ventricle here, right? It takes blood, venous return from the body, pumps into the lungs. Fontan circulation is missing this right ventricle. And this is what the anatomy looks like. This is after some surgical reconstruction. You have the inferior vena cava, superior vena cava connected directly to the pulmonary arteries. And so you're basically missing this subpulmonary pump. So this kind of circulation creates a number of problems. And it's mostly coming from something that's called the Fontan paradox. And what this means is that if you look at this difference right here, so you have low pressure in the venous coming into the RV, and there's a pressure boost into the lungs. It's missing that over here. And so your veins, your caval veins, are seeing a much higher pressure than they like to see. And so you have a high central venous pressure, and your organs are dumping this blood into the vena cava, and they're seeing this high pressure they don't like. And so these you end up with things like liver disease, multi-organ failure, and things like that. Now, on the other hand, your lungs is seeing a pressure here with no pressure boost, and so it's seeing a lower pressure than it normally wants to see, and so you have preload deficiency, and you end up having diastolic dysfunction. So this circulation is surgically constructed, and it's good for keeping the patient alive for some time, but over time this circulation begins to fail. Now there are two primary types of method of failure, and these are called the failing Fontan circulation. So one of them has low cardiac output and the other one has normal cardiac output. They both have high caval pressure, which is an indication of mortality risk. And so if you look at this plot here, you can clearly see that there's a link between mortality and the CVP, which is a central venous pressure. So the idea of a cavopulmonary support is that if we can basically substitute this missing ventricle with some kind of mechanical device, this could potentially help improve the physiology of the patient. And here's a illustration showing what that might look like. In this case, this is shown as using a Berlin heart, but you could put any device here to achieve this purpose. Now, the problem is that currently there are no existing device commercially available that is specifically designed for this application. And recently, we've shown in a paper that if you were to use a left side blood pump for this application, it has its own risks. So the central question that we're asking in this research is, if we were to design a device specifically for this application, what would the design requirements be for this device? That's what we want to answer. So the way that we approach this is we use a lumped parameter network physiology model to try to simulate a range of clinical scenarios to try to see what the results might look like and what kind of pump operating criteria that we need. And so there are two surgical implementations that we're looking at, the full assist and IVC assist. So what the full assist is basically all of the venous return goes through the device, gets pushed into the lungs. The IVC assist is only the IVC flow goes through the device, and the SVC flow is unsupported. Now, we want our simulated physiologies to be representative of the patient cohort that we're looking at. And so if you look at clinical data of these failing Fontan physiology, these patients have a combination of different vascular resistances and different ventricular functions, which are reflected as the clinically observed parameters that you see here. So this is the range that you observe in the clinics. And so the idea is that, the reason that, for example, these patients have this cardiac index is because they have a combination of these things that will result in this type of cardiac index. And so the way that we approach this, we want to create a combination of all different possible scenarios that will represent this patient cohort. And so that we can simulate a wide range of clinical cases. And so that's what we did in the simulation. And we ended up creating a total of about 1,245 patient cases with combinations of physiologies spanning across plus minus 2 standard deviation of what is clinically observed out there. And so if you look at this plot right here, the blue is the clinical observation plus minus 2 standard deviation. And if you look at all the cases that we simulated, and if you look at the range of the physiologic parameters, is shown in the red here. And so this is encapsulates the clinically observed range. And so this is a cardiac index, and you have different kind of pressures that we try to simulate. And so the idea is that our simulated cohort can cover more than 95% of the patient cases that are out there. So for each patient case that we simulated different kind of pump inputs to estimate what the outcome, the physiologic outcome may be. And so we ended up running a total of about 90,000 simulations to look at these different kind of pump support in all the patient cases. And from these simulation results, we try to identify the ones where a favorable physiology is achieved. And the way that we define favorable is that there's a set of criteria that it needs to meet. And so these are the criteria. We want to have some reduction in the IVC pressure to unload the venous pressure, but we don't want it to reduce too much, because then when you start to have very, very low pressure, you could potentially have venous collapse, and we don't want that to happen. We want to make sure that the pulmonary pressure and the SVC pressure is not too high, so otherwise you have damage to the pulmonary vasculature, or you have a high stroke risk. And also we want to see that the atrial pressure is below a certain threshold, because typically one of the symptoms in Fontan failure is that the atrial pressure begins to rise. So we look at this criteria of all these 90,000 simulations, and we identify the ones where favorable physiology is achieved, and we looked at the flow and the pressure that is going through the pump in those cases, and we congregated those points to create these regions. And so these regions basically represent the operating point of the device where it is helpful for someone, or in some of these cases. And so now what you can do is these regions can now serve as a guideline for the criteria or the operating range that your device needs to produce. And so, for example, if I wanted to design a device that is going to support in a full assist arrangement for group 1 patients, if I can make a device that can cover this operating range at different RPMs, then I'm able to offer the surgeon the maximum flexibility to be able to adjust the device to support any patient that might need this. And we can also use our results to potentially evaluate experimental devices. And so here we're looking at a Jarvik 2000 blood pump that's operating outside of the commercial operating range. And then here's another previously published experimental device. So we can look at the operating condition, a specific condition of these devices, look at their characteristics, and see how much it overlaps with these regions, and have some idea of how useful these devices are going to be for this particular application. And lastly, we can use these simulation results to try to understand which patients might be able to benefit from cavopulmonary support. And so if you look at all of the patient cases that we simulated, actually not all of them can benefit from cavopulmonary support. So some of them never end up having the favorable physiology. And so we basically we look at the patient cases where improvement was possible, and then we looked at their pre-support hemodynamics. So before they had the device, what did their hemodynamic look like? And we plotted the range here. And so cardiac index and atrial pressure and so on. So basically, these ranges represent the pre-support hemodynamic if you had this characteristic, then it is possible for you to benefit from cavopulmonary support. Okay? So if there's a patient standing in front of me, and I look at them, and I see that, let's say, their IVC pressure is lower than 12, then based on the simulation results, I would say that the cavopulmonary support is probably not going to help you. So this kind of results can potentially assist in patient selection. And with that, I'd like to thank lab members and collaborators who contributed to this project and funding sources. Thank you.